Human-Euro-computer interaction involves the study, planning, design and uses of the interaction between people and computers. It is often regarded as the intersection of computer science, behavioral sciences, design, media studies, and several other fields of study. The term was popularized by Card, Moran, and Newell in their seminal 1983 book, The Psychology of Human-Computer Interaction, although the authors first used the term in 1980, and the first known use was in 1975. The term connotes that, unlike other tools with only limited uses, a computer has many affordances for use, and this takes place in an open-ended dialogue between the user and the computer. Introduction. Humans interact with computers in many ways, and the interface between humans and the computers they use is crucial to facilitating this interaction. Desktop applications, internet browsers, handheld computers, and computer kiosks make use of the prevalent graphical user interfaces of today. Voice user interfaces are used for speech recognition and synthesizing systems, and the emerging multimodal and gestalt user interfaces allow humans to engage with embodied character agents in a way that cannot be achieved with other interface paradigms. The Association for Computing Machinery defines human-computer interaction as a discipline concerned with the design, evaluation and implementation of interactive computing systems for human use and with the study of major phenomena surrounding them. An important facet of HCI is the securing of user satisfaction. Because human-Euro-computer interaction studies a human and a machine in communication, it draws from supporting knowledge on both the machine and the human side. On the machine side, techniques in computer graphics, operating systems, programming languages, and development environments are relevant. On the human side, communication theory, graphic and industrial design disciplines, linguistics, social sciences, cognitive psychology, social psychology, and human factors such as computer user satisfaction are relevant. And, of course, engineering and design methods are relevant. Due to the multidisciplinary nature of HCI, people with different backgrounds contribute to its success. HCI is also sometimes referred to as Human-Euro-Machine Interaction, MAN-Euro-Machine Interaction or Computer-Euro-Human Interaction. Poorly designed human-machine interfaces can lead to many unexpected problems. A classic example of this is the 3 Mile Island accident, a nuclear meltdown accident, where investigations concluded that the design of the Human-Euro-Machine interface was at least partially responsible for the disaster. Similarly, accidents in aviation have resulted from manufacturers' decisions to use non-standard flight instrument or throttle quadrant layouts, even though the new designs were proposed to be superior in regards to basic Human-Euro-Machine interaction. Pilots had already ingrained the standard layout and thus the conceptually good idea actually had undesirable results. HCI goals. HCI aims to improve the interactions between users and computers by making computers more usable and receptive to users' needs. Specifically, HCI has interests in methodologies and processes for designing interfaces, methods for implementing interfaces, techniques for evaluating and comparing interfaces, developing new interfaces and interaction techniques, developing descriptive and predictive models and theories of interaction. A long-term goal of HCI is to design systems that minimize the barrier between the human's mental model of what they want to accomplish and the computer's support of the user's task. Professional practitioners in HCI are usually designers concerned with the practical application of design methodologies to problems in the world. Their work often revolves around designing graphical user interfaces and web interfaces. Researchers in HCI are interested in developing new design methodologies, experimenting with new devices, prototyping new software systems, exploring new interaction paradigms, and developing models and theories of interaction. Differences with related fields. HCI differs from human factors as HCI focuses more on users working specifically with computers, rather than other kinds of machines or designed artifacts. There is also a focus in HCI on how to implement the computer software and hardware mechanisms to support Human-Euro-computer interaction. Thus, human factors is a broader term. HCI could be described as the human factors of computers although some experts try to differentiate these areas. HCI also differs from human factors in that there is less of a focus on repetitive work-oriented tasks and procedures, and much less emphasis on physical stress and the physical form or industrial design of the user interface, such as keyboards and mouse devices. Three areas of study have substantial overlap with HCI even as the focus of inquiry shifts. In the study of personal information management, human interactions with a computer are placed in a larger informational context. People may work with many forms of information, some computer-based, many not, in order to understand and effect desired changes in their world. In computer-supported cooperative work, emphasis is placed on the use of computing systems in support of the collaborative work of a group of people. The principles of human interaction management extend the scope of CSCW to an organizational level and can be implemented without use of computers. Design principles. When evaluating a current user interface, or designing a new user interface, it is important to keep in mind the following experimental design principles: early focus on user S, and task S, establish how many users are needed to perform the task S, and determine who the appropriate users should be. Someone who has never used the interface, and will not use the interface in the future, is most likely not a valid user. In addition, define the task S the users will be performing and how often the task S need to be performed. Empirical measurement. Test the interface early on with real users who come in contact with the interface on a daily basis. Keep in mind that results may vary with the performance level of the user and may not be an accurate depiction of the typical human-computer interaction. Establish quantitative usability specifics such as the number of users performing the task S, the time to complete the task S, and the number of errors made during the task S. Iterative design. After determining the users, tasks, and empirical measurements to include, perform the following iterative design steps: design the user interface, test, analyze results, repeat the iterative design process until a sensible, user-friendly interface is created. Methodologies. A number of diverse methodologies outlining techniques for human-computer interaction design have emerged since the rise of the field in the 1980s. Most design methodologies stem from a model for how users, designers, and technical systems interact. Early methodologies, for example, treated users' cognitive processes as predictable and quantifiable and encouraged design practitioners to look to cognitive science results in areas such as memory and attention when designing user interfaces. Modern models tend to focus on a constant feedback and conversation between users, designers, and engineers and push for technical systems to be wrapped around the types of experiences users want to have, rather than wrapping user experience around a completed system. Activity theory, used in HCI to define and study the context in which human interactions with computers take place. Activity theory provides a framework to reason about actions in these contexts, analytical tools with the format of checklists of items that researchers should consider, and informs design of interactions from an activity-centric perspective. User-centered design. User-centered design is a modern, widely practiced design philosophy rooted in the idea that users must take center stage in the design of any computer system. Users, designers and technical practitioners work together to articulate the wants, needs and limitations of the user and create a system that addresses these elements. Often, user-centered design projects are informed by ethnographic studies of the environments in which users will be interacting with the system. This practice is similar but not identical to participatory design, which emphasizes the possibility for end users to contribute actively through shared design sessions and workshops. Principles of user interface design. These are 7 principles of user interface design that may be considered at any time during the design of a user interface in any order: tolerance, simplicity, visibility, affordance, consistency, structure and feedback. Value-sensitive design. Value-sensitive design is a method for building technology that account for the values of the people who use the technology directly, as well as those who the technology affects either directly or indirectly. VSD uses an iterative design process that involves three types of investigations: conceptual, empirical and technical. Conceptual investigations aim at understanding and articulating the various stakeholders of the technology, as well as their values and any values conflicts that might arise for these stakeholders through the use of the technology. Empirical investigations are qualitative or quantitative design research studies used to inform the designer's understanding of the user's values, needs, and practices. Technical investigations can involve either analysis of how people use related technologies, or the design of systems to support values identified in the conceptual and empirical investigations. Display designs. Displays are human-made artifacts designed to support the perception of relevant system variables and to facilitate further processing of that information. Before a display is designed, the task that the display is intended to support must be defined. A user or operator must be able to process whatever information that a system generates and displays. Therefore, the information must be displayed according to principles in a manner that will support perception, situation awareness, and understanding. 13 Principles of Display Design. Christopher Wickens al. defined 13 principles of display design in their book An Introduction to Human Factors Engineering. These principles of human perception and information processing can be utilized to create an effective display design. A reduction in errors, a reduction in required training time, an increase in efficiency, and an increase in user satisfaction are a few of the many potential benefits that can be achieved through utilization of these principles. Certain principles may not be applicable to different displays or situations. Some principles may seem to be conflicting, and there is no simple solution to say that one principle is more important than another. The principles may be tailored to a specific design or situation. Striking a functional balance among the principles is critical for an effective design. Perceptual Principles. 1. Make displays legible. A display unregistered trademark's legibility is critical and necessary for designing a usable display. If the characters or objects being displayed cannot be discernible, then the operator cannot effectively make use of them. 2. Avoid absolute judgment limits. Do not ask the user to determine the level of a variable on the basis of a single sensory variable. These sensory variables can contain many possible levels. 3. Top-down processing. Signals are likely perceived and interpreted in accordance with what is expected based on a user or unregistered trademark's past experience. If a signal is presented contrary to the user or unregistered trademark's expectation, more physical evidence of that signal may need to be presented to assure that it is understood correctly. 4. Redundancy gain. If a signal is presented more than once, it is more likely that it will be understood correctly. This can be done by presenting the signal in alternative physical forms, as redundancy does not imply repetition. A traffic light is a good example of redundancy, as color and position are redundant. 5. Similarity causes confusion. Use discriminable elements. Signals that appear to be similar will likely be confused. The ratio of similar features to different features causes signals to be similar. For example, A423B9 is more similar to A423B8 than 92 is to 93. Unnecessary similar features should be removed and dissimilar features should be highlighted. Mental Model Principles. 6. Principle of Pictorial Realism. A display should look like the variable that it represents. If there are multiple elements, they can be configured in a manner that looks like it would in the represented environment. 7. Principle of the Moving Part. Moving elements should move in a pattern and direction compatible with the user or unregistered trademark's mental model of how it actually moves in the system. For example, the moving element on an altimeter should move upward with increasing altitude. Principles based on attention. 8. Minimizing information access cost. When the user or unregistered trademark's attention is diverted from one location to another to access necessary information, there is an associated cost in time or effort. A display design should minimize this cost by allowing for frequently accessed sources to be located at the nearest possible position. However, adequate legibility should not be sacrificed to reduce this cost. 9. Proximity Compatibility Principle. Divided attention between two information sources may be necessary for the completion of one task. These sources must be mentally integrated and are defined to have close mental proximity. Information access costs should be low, which can be achieved in many ways. However, close display proximity can be harmful by causing too much clutter. 10. Principle of multiple resources. A user can more easily process information across different resources. For example, visual and auditory information can be presented simultaneously rather than presenting all visual or all auditory information. Memory Principles. 11. Replace memory with visual information, knowledge in the world. A user should not need to retain important information solely in working memory or retrieve it from long-term memory. A menu, checklist, or another display can aid the user by easing the use of their memory. However, the use of memory may sometimes benefit the user by eliminating the need to reference some type of knowledge in the world. The use of knowledge in a user or unregistered trademark as hidden knowledge in the world must be balanced for an effective design. 12. Principle of predictive aiding. Proactive actions are usually more effective than reactive actions. A display should attempt to eliminate resource-demanding cognitive tasks and replace them with simpler perceptual tasks to reduce the use of the user or unregistered trademark's mental resources. This will allow the user to not only focus on current conditions, but also think about possible future conditions. An example of a predictive aid is a road sign displaying the distance to a certain destination. 13. Principle of consistency. Old habits from other displays will easily transfer to support processing of new displays if they are designed in a consistent manner. A user or unregistered trademark's long-term memory will trigger actions that are expected to be appropriate. A design must accept this fact and utilize consistency among different displays. Human-Computer Interface. The human-computer interface can be described as the point of communication between the human user and the computer. The flow of information between the human and computer is defined as the loop of interaction. The loop of interaction has several aspects to it, including task environment, the conditions and goals set upon the user. Machine environment, the environment that the computer is connected to, for example a laptop in a college student's dorm room. Areas of the interface. Non-overlapping areas involve processes of the human and computer not pertaining to their interaction. Meanwhile, the overlapping areas only concern themselves with the processes pertaining to their interaction. Input flow, the flow of information that begins in the task environment, when the user has some task that requires using their computer. Output, the flow of information that originates in the machine environment. Feedback, loops through the interface that evaluate, moderate, and confirm processes as they pass from the human through the interface to the computer and back. Fit, this is the match between the computer design, the user and the task so as to optimize the human resources needed to accomplish the task. Current research, topics in HCI include, user customization, end-user development studies how ordinary users could routinely tailor applications to their own needs and use this power to invent new applications based on their understanding of their own domains. With their deeper knowledge of their own knowledge domains, users could increasingly be important sources of new applications at the expense of generic systems programmers. Embedded computation. Computation is passing beyond computers into every object for which users can be found. Embedded systems make the environment alive with little computations and automated processes, from computerized cooking appliances to lighting and plumbing fixtures to window blinds to automobile braking systems to greeting cards. To some extent, this development is already taking place. The expected difference in the future is the addition of networked communications that will allow many of these embedded computations to coordinate with each other and with the user. Human interfaces to these embedded devices will in many cases be very different from those appropriate to workstations. Augmented reality, a common staple of science fiction. Augmented reality refers to the notion of layering relevant information into our vision of the world. Existing projects show real-time statistics to users performing difficult tasks, such as manufacturing. Future work might include augmenting our social interactions by providing additional information about those we converse with. Factors of change. Traditionally, as explained in a journal article discussing user modeling and user-adapted interaction, computer usage was modeled as a human-computer dyad in which the two were connected by a narrow explicit communication channel, such as text-based terminals. Much work has been done to make the interaction between a computing system and a human. However, as stated in the introduction, there is much room for mishaps and failure. Because of this, human-computer interaction shifted focus beyond the interface, to respond to observations as articulated by D. Engelbart. If ease of use was the only valid criterion, people would stick to tricycles and never try bicycles. The means by which humans interact with computers continues to evolve rapidly. Human-computer interaction is affected by the forces shaping the nature of future computing. These forces include decreasing hardware costs leading to larger memory and faster systems, miniaturization of hardware leading to portability, reduction in power requirements leading to portability, new display technologies leading to the packaging of computational devices in new forms, specialized hardware leading to new functions, increased development of network communication and distributed computing, increasingly widespread use of computers, especially by people who are outside of the computing profession, increasing innovation in input techniques, combined with lowering cost, leading to rapid computerization by people previously left out of the computer revolution. Wider social concerns leading to improved access to computers by currently disadvantaged groups. The future for HCI, based on current promising research, is expected to include the following characteristics: ubiquitous communication. Computers are expected to communicate through high-speed local networks, nationally over wide-area networks, and portably via infrared, ultrasonic, cellular, and other technologies. Data and computational services will be portably accessible from many if not most locations to which a user travels. High-functionality systems. Systems can have large numbers of functions associated with them. There are so many systems that most users, technical or non-technical, do not have time to learn them in the traditional way. Mass availability of computer graphics. Computer graphics capabilities such as image processing, graphics transformations, rendering, and interactive animation are becoming widespread as inexpensive chips become available for inclusion in general workstations and mobile devices. Mixed media. Commercial systems can handle images, voice, sounds, video, text, formatted data. These are exchangeable over communication links among users. The separate worlds of consumer electronics and computers are partially merging. Computer and print worlds are expected to cross-assimilate each other. High-bandwidth interaction. The rate at which humans and machines interact is expected to increase substantially due to the changes in speed, computer graphics, new media, and new input-output devices. This can lead to some qualitatively different interfaces, such as virtual reality or computational video. Large and thin displays. New display technologies are finally maturing, enabling very large displays and displays that are thin, lightweight, and low in power consumption. This is having large effects on portability and will likely enable the development of paper-like, pen-based computer interaction systems very different in feel from desktop workstations of the present. Information utilities. Public information utilities and specialized industry services are expected to proliferate. The rate of proliferation can accelerate with the introduction of high-bandwidth interaction and the improvement in quality of interfaces. Scientific conferences. One of the main conferences for new research in human-computer interaction is the annually held ACM's Conference on Human Factors in Computing Systems, usually referred to by its short name CHI. CHI is organized by ACM-SIGCHI Special Interest Group on Computer-Human Interaction. CHI is a large conference, with thousands of attendants, and is quite broad in scope. It is attended by academics, practitioners and industry people, with company sponsors. There are also dozens of other smaller, regional or specialized HCI-related conferences held around the world each year, including ASIT's ACM International Conference on Computers and Accessibility, CSCW, ACM Conference on Computer-Supported Cooperative Work, DIS, ACM Conference on Designing Interactive Systems, ECSCW, European Conference on Computer-Supported Cooperative Work, Group, ACM Conference on Supporting Group Work, HRI, ACMIEEE International Conference on Humano-Euro-Robot Interaction, ICMI, International Conference on Multimodal Interfaces, ITS, ACM Conference on Interactive Tabletops and Surfaces, Mobile HCI, International Conference on Humano-Euro-Computer Interaction with Mobile Devices and Services, NIME, International Conference on New Interfaces for Musical Expression, UBICOMP, International Conference on Ubiquitous Computing, UIST, ACM Symposium on User Interface Software and Technology, IUSER, International Conference on User Science and Engineering, Interact, IFIPTC 13 Conference on Human-Computer Interaction, see also. Footnotes. Further reading. Academic Overviews of the Field, Julie A. Jacko Human-Computer Interaction Handbook. CRC Press. ISBN 1-4398-2943-8, Andrew Sears and Julie A. Jacko Human-Computer Interaction Handbook. CRC Press. ISBN 0-8058-5870-9, Julie A. Jacko and Andrew Sears Human-Computer Interaction Handbook. Maurer, Lawrence L. Baum and Associates. ISBN 0-8058-4468-6, Historically Important Classic, Stuart K. Card, Thomas P. Moran, Alan Newell, The Psychology of Humano-Euro-Computer Interaction. L. Baum, Hillsdale 1983 ISBN 0-89859-243-7, Overviews of History of the Field, Jonathan Grudin, A Moving Target, The Evolution of Humano-Euro-Computer Interaction. In Andrew Sears and Julie A. Jacko Human-Computer Interaction Handbook. CRC Press. ISBN 0-8058-5870-9, Brad Myers, A Brief History of Humano-Euro-Computer Interaction Technology. Interactions 5, 2, 44 Euro 54, 1998, ISSN 1072 Euro 5520 ACM Press. http .acm.org 274430.2744436, John M. Carroll, Human-Computer Interaction, History and Status. Encyclopedia entry at interaction-design.org, John M. Carroll, Conceptualizing a Possible Discipline of Humano-Euro-Computer Interaction, Interacting with Computers, Volume 22, Issue 1, January 2010, pages 3 Euro 12, ISSN 0953-5438, 10.1016/J&Com. 2009.11.008. Academic Journals, ACM Transactions on Computer-Human Interaction, Behavior and Information Technology, 1, Interacting with Computers, International Journal of Human-Computer Interaction, International Journal of Human-Computer Studies, Human-Computer Interaction, 2, 3, Collection of Papers, Ronald M. Baecker, Jonathan Grudin, William A. S. Buxton, Saul Greenberg, Readings in Humano-Euro-Computer Interaction. Toward the Year 2000 February ed. Morgan Kaufman, San Francisco 1995 ISBN 1-55860-246-1, Treatments by one or few authors, often aimed at a more general audience, Jacob Nielsen, Usability Engineering. Academic Press, Boston 1993 ISBN 0-12-518405-0, Donald A. Norman, The Psychology of Everyday Things. Basic Books, New York, 1988 ISBN 0-465-06709-3, Jeff Raskin, The Humane Interface. New Directions for Designing Interactive Systems. Addison Wesley, Boston 2000 ISBN 0-201-37937-6, Bench Niederman and Catherine Pleasant, Designing the User Interface, Strategies for Effective Human-Euro-Computer Interaction. 5th ed. Addison Wesley, 2009 ISBN 0-321-53735-1, Bench Niederman and Catherine Pleasant, Designing the User Interface, Strategies for Effective Human-Euro-Computer Interaction. 4th ed. Addison Wesley, 2004 ISBN 0-321-19786-0, Bruce Tognazny, Tog on Interface. Addison Wesley, Reading 1991 ISBN 0-201-60842-1, Textbooks, Alan Dix, Janet Finley, Gregory Aboud, and Russell Beal, Human-Euro-Computer Interaction. 3rd edition. Prentice Hall, 2003. http, ibook.com ISBN 0-13-046109-1, Yvonne Rogers, Helen Sharp and Jenny Preece, Interaction Design, Beyond Human-Euro-Computer Interaction, 3rd ed. John Wiley & Sons Limited, 2011 ISBN 0-470-66576-9, Helen Sharp, Yvonne Rogers and Jenny Preece, Interaction Design, Beyond Human-Euro-Computer Interaction, 2nd ed. John Wiley & Sons Limited, 2007 ISBN 0-470-01866-6, Matt Jones and Gary Marston. Mobile Interaction Design, John Wiley & Sons Limited. External links, Bad Human Factors Designs, the HCI Wiki bibliography with over 100,000 publications. The HCI bibliography over 100,000 publications about HCI. Human-Centered Computing Education Digital Library, HCI bibliography with a list of about 100 HCI organizations worldwide.